Kia ora and welcome to video 5 in the series Delightful Differentiation. The problem today is a related rates question. If you haven't seen related rates problems before, it will be quite tricky. I know that my class currently hasn't done them. Having said that, you can follow through the solution and learn a little bit. Basically, we need to connect the rates in the question together. So we've got a rate that the sides of this octahedral are increasing at, and we need to find the rate that its surface area is increasing at. We've also been given information about the volume. Normally with these problems we'd be given time, or we'd be given how long the side length is, but in this question we actually have to work that out too. So the volume is 9 root 2. We can use that information to find the length of the side, and then we can use that information along with the connection of the rates using differentiation skills, of course, to work out the answer to this question. There's no shame in looking it up on Google. I actually had to search up what an octahedral was. The picture there is pretty accurate. The faces there are equilateral triangles, and you can think of them as two pyramids. Anyways, enjoy this problem, and we'll catch you next week for another 5 problems. All the best. Okay, this problem is a related rates question. The reason for that is we're given a rate in the question and we're asked for another rate. So we've got to connect these in some way, which means we need to connect the variables. These are excellence problems in NCEA, although this one is a particularly difficult one, hence why it features in this series. The first thing to note is we're talking about the surface area of the crystal. So we need a formula for the surface area. And we also need to introduce an independent variable. Now the question talks about the sides increasing. Sides are increasing at a rate of 0.25 centimeters per minute. So we bring in the variable for the side. Let's just draw over this shape here. It's made up of equilateral triangles. I guess you'd probably be defined an octahedral crystal in an exam situation, but I just had a quick Google of it to make sure I was fully understanding what it was. It's made up of equilateral triangles. So the side length there, S, is the same as that side length there, S, which is the same as the other one, which I'm not going to put on there because it will just clutter the diagram. So all those angles there are 60 degrees. It also means that we can cut those triangles in half, which I'm going to do. I'm just going to hide the side here, just so that we can think about going into the middle of the crystal. Let's say the middle of the crystal is about there. From this point, which is the midpoint of the side, I'm going to go in parallel to this side, and then straight up to the top, and that's going to generate a right angle triangle. Why am I doing that? Well, I want to find the volume of the crystal. The question says find the rate at which the surface area is increasing when the volume is 9 root 2. So first thing is I'm going to find the volume expression for the crystal. It's made up of 2 pyramids, and the volume of a pyramid is similar to the volume of a cone. It's a third times the base area multiplied by the height. And then it's times 2 for this because it's actually 2 pyramids. Now, thinking about the base area of the pyramid, it's a square, S by S. And then the height, well, we need the height in terms of S, and that's why I've drawn this right angle triangle on. Okay, the right angle triangle there goes into the center of the pyramid, and this diagonal here can be found using another right angle triangle, which is a sloping one on the surface of the crystal. So if we just pull that right angle triangle out, the hypotenuse is S and the base of it is S over 2. And then we can use Pythagoras to find this side, which is the slanting side of the face. Okay, so to do that, s over 2 all squared plus x squared is equal to s squared. X squared is the same as s squared minus s squared over 4, which is 3/4 of s squared. So our diagonal there, we could find x, but it turns out we need x squared, is found. And then we've got that standing up triangle inside, where that's the height of the pyramid. And then that is also s over 2, because it goes from one side into the middle. And then that one there was x. To find the height of the pyramid in terms of s, again Pythagoras, h squared is equal to x squared minus s over 2 all squared. And hence why I didn't find x, because I actually needed x squared in this. H squared is equal to 3/4 of s squared minus s squared over 4. Okay, 3/4 minus 1/4 is 1/2, so it's s squared over 2. And therefore the height of the pyramid is equal to s over square root 2, if we square root that expression. Okay, that's the hard part of this out of the way, the visualizing of the octahedral and the right angle triangles that are in there. Because of the equilateral triangle faces, we can split the face into bits, into two parts, which are two right angle triangles. And we can use the slanting side, slant side there to, highlighting the crystal didn't really work, did it? To find the height in terms of the side length. Okay, so s over root 2 goes into our pyramid expression. And this is before we've done any differentiation. Multiplied by 2. Now the volume we're told in the question is 9√2 at this particular instant where we're trying to find the rate. So if I make that 9√2 as well, and then multiply both sides by root 2 and also by 3, I'm going to get 9√2 times root 2 times 3. I don't know why I'm inconsistent with my times being dots or time symbols. That's annoying me. Equals... Oh, and also divide by 2 is equal to s cubed. So working that out, root 2 times root 2 is 2, which cancels with the denominator 2. S cubed equals 27. We know we're kind of onto something here when we get a nice answer. It's not always going to be nice, but kind of suggests we're doing something right if we get s is equal to 3. So, rewording the question, find the rate at which the crystal's surface area is increasing when s is 3. So when the crystal has got to a size with the side lengths of 3. Okay, we're going to have to do some differentiation. Surface area is the rate we want to find. So if we say S equals surface area, I'm going to make it a completely big S to distinguish it from the lowercase s. And we want ds dt. Related rates problems, if you've never seen them before, we connect the rate in the question with the rate that we're trying to find. So the rate in the question is this one. It's a given rate of ds dt. It's the rate that the sides are increasing. So ds dt, lowercase s. Notice the units as well, centimeters per minute. So any variables need to be in centimeters and minutes. Sometimes they mix up the units to trip you up. So we know that ds dt is equal to 0.25. Okay, so we want this rate of change of the surface area, and what we're going to do is multiply ds, oh gosh, this is really bad, d capital S, d little s, with d little s over dt. Those are the two rates we merge together, because if we multiply those together, we get the rate we need. Okay, so ds dt is in the question, 0.25. The rate that we need to be able to work out the one that we want is this one. That's the related rate. So where have we got a surface area expression? Oh, we haven't yet, because we've just found the volume expression. So let's go back to our shape, and now we think of the surface area of the crystal. Okay, surface area, we've got 8 equilateral triangles, or we've got 16 triangles like that, because that there was half of the face. And we know what the height is because we worked out x, so we can use half base times height for that. Okay, the surface area expression that we want is equal to 16 lots of a half times base, s over 2, times height, which was x. Turns out I did have to take the square root of x eventually. Square root of x squared, root 3 over 2s. Okay, this simplifies because there's a 16 and on the bottom there's an 8, 2 times 2 times 2, so 16 over 8 is 2. We have an s squared, which kind of makes sense because it's a surface area, and we have root 3, 2 root 3 s squared. Okay, that comes down to here, or not quite. The surface area is 2 root 3 s squared, but we want to differentiate that with respect to little s. Okay, so remove this thing. We're trying to find it now. That's going to be equal to 4 root 3 multiplied by s. And the question told us some information about the volume, which meant we knew what s was. So at s equals 3, when the side length was 3, the surface area is increasing at a rate of 4 times root 3 times 3 times a quarter, which is divided by 4. So the answer is 3 root 3. And you can evaluate that as a decimal if you'd like. Surface area is centimetres squared, and time is in minutes, as I said before, so we're consistent. Yeah, that problem had a lot going on. Some variables we had to relate together, a complicated diagram, but it is kind of formulaic in its nature, because with all related rates problems, there's a rate that we're trying to find, there's a rate that we're given in the question, and there's just that connecting rate. Okay, and the connecting rate for us, ds, or d capital S divided by d little s, was found as soon as we connected the rate, the variables, capital S with lowercase s. As soon as we've got that connection between those variables, we can find its derivative and then chuck it into our related rates equation.